energy states for the vibrational mode. Rotational mode I have said this is the fundamental one. So, from the basic level to the next level, okay, change in the energy, and then you have to equate it to the energy of the emission, photon emission h nu. So, that should give the corresponding wavelength. So, this is how the what you can say the corresponding emissions that are coming out of certain gases are actually fundamentally happening. So, basically what they do is there is, when you have certain energy which is incident, okay. So, these can actually absorb this energy and can get excited to higher energy levels, and after some time they again jump back to lower energy levels, resulting in emissions. Okay. So, this emission will happen in a certain frequency band for certain gases, and that is actually calculated like this from the quantum mechanics. Okay. So, a very good morning. So, today we will continue our discussion related to the electronic energy levels that we had started yesterday. So, we had used the Coulomb's potential energy constraint and showed that the corresponding values of the electron energy from the quantum mechanics by solving the Schrodinger's equation is obtained like this, where m is the mass of electron, c is a constant. So, if you plug in all the constants for electron, you get the resulting expression as minus 13.6 by n square. So, where n is a quantum number, now I mean as correctly pointed out yesterday. So, this becomes a 3-dimensional problem. We have to solve the Schrodinger's equation in theta, phi and r. So, the corresponding quantum numbers in the theta and phi direction will be L and m, and the corresponding quantum number in the r direction is n, and the energy level here, the value of magnitude of energy is found to be a function of only n. So, you find again degeneracy now, which is little bit on the higher level of degeneracy that you saw in the rotational problem. Okay. In rotational problem you had only 2 quantum numbers, now you have an additional quantum number. So, an additional level of degeneracy. So, these are the constraints on the quantum numbers. So, that means n should be greater than or equal to 1, n should be greater than or equal to. So, these are the n is related to the quantum number L through this expression here, and the quantum number L is related to m through this expression. Okay. So, therefore, let us work out what are all the different quantum states starting from for the case n equal to 1. Okay. So, for n equal to 1, now let us look at all the degenerate states possible. So, what is the value of L? So, and what are the values of L and m? So, m, magnitude of m should be less than or equal to L. Okay. So, in this case if n equal to 1, the value of m L should be 0, right. So, n should be greater than or equal to L plus 1. So, if L equal to 0, then n is greater than or equal to 1, which is satisfying the condition. And if L equal to 0, what is the value of m? Should be 0. Okay. So, therefore, the degenerate state for n equal to 1 is basically L equal to 0, m equal to 0. Okay. So, this is one quantum state, right. So, we will call this corresponding wave function corresponding to the value of n, L and m, we will designate it as 1, 0, 0. So, this gives a particular quantum state, and for this the particular energy, if you substitute n equal to 1, will be minus 13.6 electron volts. Okay. So, this is one quantum state. Now, you can just expand this for n equal to 2. So, for this case, what are the values of L? So, if L equal to 0, n is greater than or equal to 1. So, you have 0 is possible, and L can be also 1, because n can be greater than or equal to 2, in this case n equal to 2. So, L equal to 1 is also a possibility, correct. So, we can have also 1. So, again for L equal to 0, now we have values of m, that is 0, and for L equal to 1, 0 plus 1 minus 1. So, m magnitude of m can be less than or equal to n. So, 0 is also a possibility. So, therefore, in this case how many quantum states do you have? 1, 2, 3, 4. So, 4 quantum states having the same value of energy. Okay. So, what is the value of energy for this case? Minus 13.6 by 4, 3.4 electron volts for n equal to 2, and for n equal to 1 minus 13.6. So, therefore, the possible quantum states for this, so this shows degeneracy if n equal to 2. So, we have 2, 0, 0 corresponding to n equal to 2, L equal to 0, m equal to 0. Then we have 2, what are the possibilities? 1, 0, we have 2, 1, 1, we have 2, 1 minus 1. Okay. So, you have basically 4 wave functions with the same value of energy. So, this is again showing classical degeneracy. So, like this you can keep writing the quantum states for other values of n equal to 3, 4, 5. So, what I am going to give you is a convention that people are using in filling electrons according to the orbitals. So, I will just give you what will be the quantum number and what is the corresponding convention people use or denote this as an orbital. So, if you are talking about L equal to 0, this corresponds to what we call as orbital s. Okay. So, L equal to 1 is the orbital p, we have SPDF. So, we have L equal to 2, L equal to 3 df, and then what else? G, we have an orbital G also, SPDFG. So, what these convention means, that each denote a particular value of quantum number L starting from L equal to 0 to L equal to 4. So, therefore, now you can looking at these quantum states, you can clearly understand how these orbitals are filled. For case of n equal to 1, L equal to 0, m equal to 0. So, what is this orbital? Okay. So, we will I will just draw the corresponding energy. Okay. So, we have n equal to 1, which is denoted by the wave function 1, 0, 0. So, L equal to 0 is what? S orbital. So, we have therefore 1 s. So, this quantum state denoted by n equal to 1 basically has only one wave function. So, which is called the 1s orbital. Okay. So, next, so this has the energy of minus 13.6 electron volts. The electron occupying this particular quantum state is denoted by 1s electron. Okay. So, if you go to n equal to 2, Okay. So, we have in this case 4, but we have how many L quantum numbers? 0 and 1. So, basically we have 2 orbitals here. So, one is the s orbital, the other is p orbital. Okay. So, we call this as therefore 2s 2p, because this 2 comes from the value of n. So, therefore, we have 3 quantum states corresponding to 2p and 1 quantum state corresponding to 2s, or in other words you can have 3 electrons occupying 2p and 1 electron occupying 2s, right. So, in fact, if you are including the spin plus half minus half, so we have additional degeneracy. So, in 2p instead of 3 you can say 6 electrons can occupy and 2 electrons can occupy the s orbital, because we have plus half minus half spin is also there. Okay. So, actually speaking you have in this case 8 quantum states including spin. So, in this case you are talking about 2 quantum states including spin. And then if you go to the n equal to 3, now you can do some calculation and tell me what are all the possibilities for n equal to 3. What are all the values of L? 0, 1, 2 and corresponding values of M. This is 0, this is 0, plus 1, minus 1, and for 2 0, plus or minus 1, plus minus 2. So, therefore, what are all the orbitals that we have? 3s, 3p and 3d. Okay. And what is the corresponding value of E? 13.6 divided by 9, 1.51 minus 1.51 electron volts. For n equal to 2 we have minus 3 point how much? 4 electron volts. So, how many quantum states are possible for n equal to 3? So, 1, 2, 3, 4, 5, 6, 7, 8, 9 into 2 for the spin. So, we have 18 quantum states including spin. So, this is to just give you an idea, you know. So, when you do chemistry you are not dealing with quantum mechanics, you are just directly taught the orbitals, how they occupy, but the orbital is only a convention coming from the quantum mechanical states. Okay. And I mean you asked, one of you asked the question about the emissions. So, now how can we talk about emissions in the case of the electronic energy level? So, what happens when the electron from a higher energy state, from a higher quantum state jumps to a lower quantum state? So, this results in the emission of a photon h nu, and therefore, how do we calculate h nu? H nu is basically equal to delta E from the higher quantum state to the lower quantum state. Okay. So, therefore, in general the emission of photon can happen when you have 13.6 1 by n2 square minus n1 square. Okay. So, electron volts. So, therefore, you can calculate what is the frequency or wavelength of the photon emitted depending on which state from to which state the electron is actually coming down. Okay. So, this kind of summarizes all the basics, whatever is you just need to understand before we go to the next topic. So, what we will I will do now. So, just before I stop the quantum mechanics, I will give a small exercise where we again go back to our quantum well. So, let us consider again the 1D quantum well. But now the difference is, instead of having an infinite well, let us look at a well which is having a finite potential barrier height. That means so in the one dimension our coordinate starts from x equal to 0, the width of this well is d, right, and you can talk about say an electron trapped within this well, but this well is not infinitely deep. Deep means this is not coordinate, this is just energy or potential energy required to escape this constraint. Okay. So, in this case let us assume that the height or potential barrier width or potential barrier height is V. Okay. So, V is not infinity, it is finite. So, inside this well, that is between x greater than 0 less than d, there is no potential energy constraint on this particle or electron. So, this can freely move about inside the well, whereas if you are talking about x less than 0 or x greater than d, your potential energy constraint is finite, equal to V. So, for this case write down the Schrodinger's equation, use separation of variables. So, only in the spatial direction write down the solution. So, now how many solutions you will have? So, for the case of infinite potential well, how many solutions you had? You considered only the domain x 0 to d. Outside the wave function is 0 because it cannot get out of the well. So, you did not consider the domain outside, you considered only within the well. So, you had one solution. Okay. So, now there is also a possibility the electron can come out of the potential well and they can therefore exist for the other dimension. So, that means you have to also find a solution for x less than 0 and x greater than d, right. So, now you will have 2 more solutions. So, therefore, 3 solutions you will have. Okay. So, let us first write down the equation for x greater than 0 less than d. In this case, the spatial equation, the ODE, will be d square psi by dx square. Then what do you have? Minus E psi equal to 0, because u equal to 0. So, the solution for this, if you write in terms of exponential function, you can also write in trigonometric function or exponential function. So, this will be something like, let me use the constants b. Yeah, I will use b exponential what do you have? You have a right running wave, you have a left running wave. So, right running wave, so we have an imaginary number I, right. So, what do you have? Plus ikx or minus ikx for the right running wave? Please check whether it should minus ikx or plus ikx.
Right running wave is minus ikx.
Yeah. So, we will write it as minus ikx plus c exponential left running wave ikx. Okay. I think it has to be the other way. Plus should be for right. So, plus should be for the right running wave and minus should be for the left running wave. Okay. So, that means inside the potential well you can have electrons running to the right or left constrained by this potential well. We have still not come to the boundary conditions, we will do that. Now, x less than 0. So, let us call this solution first solution as psi 1 subscript 1, okay, because this wave function is going to be different from less than 0 and greater than d. So, for less than 0 you can again write down solution some a exponential ikx plus something like a prime exponential minus ikx. Now, we have to be careful to differentiate this k and this k, right, because now the Schrodinger's equation for this case will be what? We will have also the potential minus V minus, what is the sign? So, if you minus of E minus V, right, psi. So, this is the correct representation here. So, therefore, the difference here, let us say this is k, let us say this is k1, this is k2. We can also write in a slightly different form, I am just making you aware, so that you are not all the time doing the same thing. So, you can also write this as plus V minus E. So, So, in the case what will happen to the solution? It will be still exponential, but the imaginary number will not be there, or in other words, in terms of trigonometric function, it becomes hyperbolic sine plus hyperbolic cos will be the solution. Okay. Or in terms of exponential function, we will not have this I. So, rather you will have just real part.
But will be the only then when will be the V will be greater than E.
Yeah, I mean, but we are just writing it in a form like this, so that we dealing with now real part, not imaginary part. Why? Because we will just apply a condition now. The condition is that if you are considering x less than 0, a wave which is basically existing on this part, and if you are talking about x going to minus infinity. So, what will happen to one of these terms? So, this is x minus infinity. So, this will be exponential of infinity minus infinity, whereas this will become exponential of minus infinity plus infinity. So, exponential of infinity is what? Infinity. Okay. So, in order to make this finite, therefore, a prime has to be 0. So, this is why we want to work with the real values here. So, that is why we have just rewritten the equation such that we will have the real roots, and then we will apply this condition that going to minus infinity exponential minus k1 x goes to infinity, which gives a prime equal to 0 in order to make the solution finite. So, therefore, what we get here is psi 2 of x is equal to a exponential k1 x. So, now how is k1 related to E and how is k2 related to E here? So, how do we relate, for example, here? So, if you recollect, E is equal to h bar k the whole square by 2m. So, when there is no potential energy constraint u equal to 0, this is what we got for the relation between E and k. So, therefore, k essentially is what? Square root of E by 2m E by h square. Okay. Whereas, in this case x less than 0, so your k1 will be square root of 2m, instead of v we will have v minus e. Okay. Okay, let us also be consistent with the, so we will use this as 1 for x less than 0, because we have used k1 here, and let us do this as 2. So, this becomes 1 x less than 0, right. So, similarly, we have to do this for x greater than d. So, let us write this as psi 3 x. So, in this case we will have the same Schrodinger's equation as represented by this form, and the solution we will write this as some d k 3 x plus d prime x 3 x. Once again we can put the condition x going to infinity. Okay. So, your exponential k 3 x goes to infinity, and therefore d equal to 0. So, therefore, your, or let me call this as d prime and d. So, that the d prime part gets eliminated. The d prime goes to 0, therefore, psi 3 x will be d exponential minus k 3 x. And what is k 3 here? Once again 2m v minus e. So, therefore, you can replace k 3 with k 1, both are same. Okay. So, now how many unknowns are there? So, psi 1 we have a is the unknown constant, psi 2 we have two constants b and c, right, and psi 3 we have constant d. So, totally we have 4 constants, 4 unknowns. So, now we have to look at the boundary conditions. So, for the case of infinite quantum well, we simply put at x equal to 0 and x equal to d, the wave function is 0. But in this case we continue to have wave functions for x less than 0 and x greater than d. Okay. So, you are talking about a wave for x less than 0. So, you may have a wave, and this now can continue like this and keep going, right. So, for x less than 0 you have a wave, now x between 0 and d, this wave has to continue, and then x greater than d, again this has to continue. So, therefore, there has to be a continuity of the wave function coming from the solution psi 1 with psi 2 and psi 3, especially at the boundaries. So, at x is equal to 0 and x equal to d, the wave function psi 1 and psi 2 has to be continuous, they have to be same, and similarly at x equal to d, psi 2 and psi 3 have to be same, and not only the value, but also the slope also has to be equal. So, now therefore, we will have 4 conditions. So, one on the wave function, one on the slope at x equal to 0, the other at x equal to d. So, we will have 4 equations to solve for the 4 unknowns. Okay. So, therefore, if you put the condition at x equal to 0, psi 1 equal to psi 2. So, this will give you a equal to b plus c. You can check this later, but I am directly giving you the boundary conditions. So, this is your condition 1, then the fact that the slope also should be equal at x equal to 0 gives you that k1 a should be equal to I times k2 into b minus c. Please check this later. Similarly, at x equal to d, psi 2 equal to psi 3 should give you b exponential I k2 d plus c exponential minus I k2 d should be equal to d exponential minus k1 and k3 are same. So, we can use k1 times d. Okay. Similarly, the slopes d psi 2 by dx will be equal to d psi 3 by dx. So, you can continue this exercise, find the constants, and therefore, we can find out the actual quantized energy states. The the magnitude of these energies are related to these numbers k1 and k2. So, by solving these equations we should be able to therefore find out the required values of energy. So, just I am giving you a little bit more complex problem, okay, compared to what we have done previously. So, you can do all kinds of things, because now we are dealing with wave effects. Okay, for example, there could be another configuration where you have what is called as a barrier instead of a well. You can have a potential barrier, and you can have a wave which is coming this way. So, it faces this barrier. Now, what happens is you can also have a reflection of this wave from this barrier. Okay. Some portion can be transmitted. Similarly, inside you have right running and left running waves, and again on this side you can have incoming and outgoing waves. Okay. So, you can apply the Schrodinger's equation for this kind of barrier problems also, and you can actually see that there is a finite wave which is actually transmitted across the barrier when you solve this equation. Although there is a barrier, there is a boundary, the wave actually goes right through. So, this effect is called tunneling effect. This is a very important phenomena in quantum mechanics. So, when you keep a barrier of a finite width, and you will also see that the transmission of this wave through the barrier depends on the width of this barrier. If the barrier is too wide, it cannot tunnel through. Okay, very thin width it can tunnel through. So, why this tunneling is happening? It is purely described by quantum mechanics. Okay. So, you can extend the problems to include also a barrier, and you can also see how this tunneling happens and so on. Okay. So, we will not have much time to go into all these details, but nevertheless I hope now you have some basic idea about how to use the Schrodinger's equation, solve simple problems. And what I would like to do is then move on to the next topic.
So, can we consider the incoming wave as a right running wave?
Right. The incoming wave should be a right running wave, the reflected wave is a left running wave, and similarly inside, okay, and the other side also.
So, can we have the…
So, now that, yeah, exactly. So, now that you know the convention for the right running and left running waves, you do not even have to again start from the scratch. You already know the right running wave should have plus ikx, left running wave is minus ikx. So, directly use only those waves that you are considering. Yeah. So, then it becomes much easier for you. I think if you take any fundamental book on quantum mechanics, this kind of barrier problems and finite potential well problem should be worked out. So, then you will be able to easily understand. Okay. Right. So, the next part what I would like to cover is to look at the extension of this quantum mechanics to a more practical system. Okay. So, therefore, we will maybe in the next 3 classes or so look at little bit of solid state physics. So, we have considered in the previous case electron waves which are subjected to some simple potentials, and how the wave function looks, how the energy states get quantized and how to calculate them. But for us for heat transfer, how does this affect our heat transfer problem. So, we have to look at a more practical configuration where electrons are confined in crystals, in solids. So, how does the quantum mechanics decide these quantum states in a more complex configuration. Okay. So, I will what I will do is I will not be able to solve the equations for more complex cases, but I will introduce you to the problem and then I will give you the solution, okay, and mainly to let you know the real scenario. Okay. So, therefore, when you extend this the free electron model, which is what we have a quantum well, to a solid crystal structure. Okay. So, we have a crystal or crystalline solids, we describe by what is called as a lattice. Okay. So, how do we define this kind of a lattice? Is just a regular arrangement. You can have some fixed points in space and fixed separation, and then you can just put some points, and now you can arrange atoms on these onto these points. Okay. So, depending on the kind of arrangement that you have different crystals. Okay. So, you can now start building therefore unit cells based on this. So, some simple cells could be something like this, where you arrange atoms at the corners of this particular unit cell. So, you can have a simple structure. You can also basically have a more complex arrangement. So, you can include something like this, and you can have another one. So, you can connect like this, So, these are all called unit cells. Okay. So, these fixed points are called lattices, lattice points, and if you put the atoms to these lattice points, so this is called bases. Okay. So, if you put the atoms to these fixed lattice points, this is called bases. So, therefore, your crystal actually is nothing but lattice plus bases. So, when you arrange the atoms onto these lattice points, then you form a crystal, and this crystal will have a periodically repeating structure. So, we actually look at a unit cell of a crystal, and then from there we can apply periodicity principle. So, now I do not think we will have much time to, but let me give you a brief idea about what happens to electrons inside such a crystal structure. So, we are now moving from free electrons subject to some arbitrary potential to a real scenario. So, in this case you can model, a very popular model is called the Kronig-Penney model to describe the electrons in a crystal. So, that means you have atoms, and these atoms, interaction between the atoms, now we know that there is a potential. So, we use the harmonic potential or whatever it is, but nevertheless the interaction potential between the atoms is now the potential constraint. So, between these atoms you have this kind of potentials, and this is now going to be periodic and repeating. Okay. So, therefore, we can consider a unit cell to model the electron motion. Now, the electrons could be confined within this potentials. Okay. So, the electron that you have in a crystal now is actually constrained by the potential due to the interaction between two atoms, okay, and that is described by the chronic penny model. Now, the chronic penny model simplifies this kind of interaction potential, that which you have is a more complex one, to a simple potential like this, rectangular potentials. Okay. So, you can have a coordinate say x equal to 0, and let us say this is x equal to minus b, the width of this potential in the negative x direction, and this width between the potentials or spacing between the potentials could be x equal to a, this is then a plus b. Okay. So, this is b here. So, this could be like a quantum well, okay, which is of width a, and this is again b. So, therefore, now it becomes repeating. So, as you go from 0 to a plus b, you can work out a periodic, solve the Schrodinger's equation for this periodic potential, and that becomes repeating, so on and so forth. So, this is the simplification what chronic penny model does to the actual electrons inside a periodic crystal structure. So, then the Schrodinger's equation for this system is solved. We will maybe look at the solution tomorrow, because now we do not have enough time. Okay. So, nevertheless, we will do this tomorrow, and then we will also look at therefore, the electron energy levels in an actual crystal, how they look from what we have as a simple free electrons, how the energy levels are modified by means of the crystal structure. Then we will look at also the vibrational energy levels of not electrons, but due to the vibration of these atoms inside the crystal structure. So, that is the phonon energy levels. So, these two we will study, we will study how their energy levels are actually looking inside the crystal structure. So, that is the starting point for our heat transfer calculations. So, where we use statistical thermodynamics. So, first we have to understand the basic energy levels of electrons and phonons in solids, then we apply the statistical thermodynamics to convert these microstates to a macroscopic properties. So, in the next I would say about 6 to 9 classes, slowly we will transition from the microscopic state to the classical state. Okay. Thank you.